This is the inverting configuration practice problems on page 65. This is practice problem 2.4. And in this practice problem, we are given this op-amp inverting configuration circuit. And the question asks for use the circuit below to design an amplifier with the -10 gain. So just to review, that means that the gain, which is equal to V out divided by V in, is equal to -10. And also we are required that the input resistance is 100 kilo ohms, and we are asked to find out what is the value of R1 and R2 that allows these to happen. Okay, so first we can say that we can treat this op-amp as an ideal op-amp, and the reason is because although we have previously derived this equation that calculates the gain if the op-amp is not ideal, meaning A is not infinity, but the thing is, as we have done some practice problems in previous video, we have come to the conclusion that you can change this you can change open loop gain A by a lot, and you can times 100, but the G does not changing much. So the conclusion that we talked about was saying that, well, you can treat, even if the op-amp is not an ideal op-amp, you can treat it as if it was an ideal op-amp, because that would be a very close enough and very accurate approximation. So that's what we are going to do here. So we're going to treat this as if it was an ideal op-amp, because that's a very close approximation, which means that in an ideal op-amp, there is no current that goes into the input terminals. If that is the case, it means that the current here is equal to the current here. So let's call this name of this current, just call that I1. And we know from this KCL that I1 is equal to this voltage minus this voltage divided by R1. So it is V in minus V minus divided by R1. And another way to say this is that it is also, this current is equal to that voltage minus this voltage divided by this resistance. So it is V minus minus V out divided by R2. Now, another aspect of the ideal op-amp says that when there is this ideal op-amp, you are having a virtual short circuit between the two input terminals. So here is 0 volts, and in the ideal op-amp there's a virtual short circuit, so over there the V minus also is 0 volts. So we replace this V minus with 0. So V in minus 0 divided by 1 is equal to V minus, so just 0 minus V out divided by R2. We can do a cross multiplication. So we can say that this R2 times V in is equal to -R1 times V out. So we know that the gain is equal to V out divided by V in. It's equal to -R2 divided by R1. So this is something we have found before in the past, but the thing is, it's better to actually write out the equation and solve for it. That's much better than just memorize it. So now we kind of have a better intuition of how this gain works. And so we are told that this gain has to equal -10. So in this case, the minus signs, they cancel out, so we know that R2 over R1 is equal to 10. So we're just going to know this relation. We just hold it there for 1 second. We'll come back to this. So there is another condition that says that the Rn, which is input resistance, is 100 kilo ohms. So what does this mean? This means that if you apply any test signal, in this case we call the name of this test signal, we call it Vn. If I attach it to this test signal Vn, if I attach it to here, there are two things we can know. We can measure this voltage here, is called the Vin, and we also can measure this current that flows in, we call that In. And so because of Ohm's law, we can say that Rin is equal to Vin divided by In. Now, in the case of this circuit, we can clearly see that, there is, okay, so let's clean this up. So we can clearly see that if I apply this test signal to this Vn, there's a current goes here through this R1. Then what happens? Then there's a virtual short circuit due to the ideal op-amp, and it connects back to this ground. So as we can see, the only current path that encounters this input resistance, the only resistor contributing to input resistance, it is this R1. So then we can say that R1 is equal to Rin. So we know that R1 is equal to 100 kilo ohms. So we have found the first resistor. And so because R2 divided R1 is equal to 10, which is equal to 100, we plug in this 100 kilo ohms here, then we can say R2 is equal to 10,000 kilo ohms. It's R2 is equal to 1,000 kilo ohms. So I just rewrite that to say that R2 is equal to 1 mega ohms. In the problem 2.5, it says that it gives us two circuits, one on the left and one on the right. The name of this circuit on the left is called the op-amp circuit, and the name of the circuit on the right is called the trans-resistance amplifier. And the question tells us that these two circuits, they are behaving equivalently to each other. So then what the question is saying is, we're going to take an input signal, which is this here, and we attach it to the input of the trans-resistance amplifier. So here is attached to here. And the question asks, what is V out? So to find V out, what we can do is we can attach the input, we'll just attach it to the trans-resistance amplifier. So just copy everything, and then we're going to attach it to here. Okay, so what we can see, what is happening is the trans-resistance amplifier, what it does do is it measures the voltage, it measures the current going through this resistor there, and it multiplies it by a number called Rm, and it produces this output voltage called Vout is equal to Rm times In. So this is a voltage controlled voltage, this is a current controlled voltage source. So current controlled voltage source. So the question tells us that we don't have any input resistance. So this op-amp is not having an input resistance here. So there is a theoretical path that goes to ground. If we take advantage of the what's called the virtual short circuit, it's important to note that no current actually flows through the op-amp in this way, but there is a virtual short circuit such that the open loop gain is so high in the ideal op-amp that the voltage here is equal to voltage here. So we can pretend that there is a path of the input signal that goes from Vn to ground. There is no input resistance, so we can say this is 0. So that is what this means. Then there's also another thing they tell us about this circuit they have given us. They said that there is no output resistance, and likewise it still says. So if I apply the test signal to Vout, there is no resistance I'm encountering to reach the op-amp. So that's what this means. So we can say that both Rin and both Rout is equal to 0. So if this is replaced with 0, or called like essentially the virtual short circuit, so I'm going to draw this with dotted line here for virtual short circuit. Remember, op-amp has having not an actual short circuit, but it's a virtual short circuit between the input terminals. So if I put this virtual short circuit here, you can see that theoretically the path for the current goes, the path for this input signal just can reach, eventually it can reach to the ground without encountering any resistance. So we can see that In is equal to 0.5 milliamps. So then Vout is equal to Rm times 0.5 milliamps. So we have one more unknown, which is this Rm. What is Rm? So if we look at, there are two equivalent circuits. The textbook tells us that these two circuits behave equivalently to each other. So as we can see here, I'm going to replace it with the virtual short circuit here, because Rin is 0. So virtual short circuit, not an actual short circuit, but a virtual short circuit. So we can see here that there is some kind of, I guess, mechanism, if you will, that converts Vin into In, and then there's another mechanism, if you will, that converts In to Vout. And the translation to go from In to Vout is through this resistor here, or I guess resistance value there. So let's talk about the first mechanism. What is the translation from Vin to In? Well, if I apply a test signal here, call it Vin, and then just attach it to there. If I attach this test signal to there, I will measure the Vin. I can also measure this In, and I can say that Rin is equal to Vn divided by In. Now we are told that Rin is equal to 0. So now we can say that because Rin is equal to 0, then we don't have to worry about this translation from V in to I in. So likewise here, there's no input resistance here, so we don't have to worry about the translation from V in to I in. Now what about the other mechanism that converts R in into V out? The conversion from I in to V out is through this Rm value. So let's look here. In the virtual short circuit assumption, V in is also having a path nearby to ground. So we can say that V out is equal to 0, which is the V minus, the virtual short circuit, plus I in multiply 10 kilo ohms. So in this case, the translation from I in to V out is through this 10 kilo ohm resistor. So 10 kilo ohm resistor is the translation factor here. Likewise, the translation factor from I in to V out on this circuit on the right is through Rm. So we have concluded that this 10 kilo ohm is, because the left circuit is, we are told it behaves equivalently to the right side circuit, then we can conclude that this 10 kilo ohm resistor is Rm. So now we know V out is equal to Rm, which is 10 kilo ohms multiply 0.5 milliamps. The kilo and the milli cancel out. So what are we left with is V out is 5 volts. This is practice problem 2.6, and it's given us a circuit with some labels of what some voltages and currents are, and it says that for this circuit determine V1, I1, I2, V1, V out, IL, I out, the voltage gain, V out divided by Vn, which is the like a closed loop gain, voltage gain, and then find out the current gain, which is IL divided by I in, and also find out the power gain, which is P out divided by P in. So first of all, virtual short, remember, in the ideal op amp, this voltage is same as this voltage. It's called virtual short. So then we can say that V1 is equal to V plus here. So V1 is equal to 0. Okay, 0 volts. So we have found the first one. Next, we are asked to find out what is I1. So I1 just says that I1 is equal to Vn minus V1 divided by 1 kilo ohms. So it's equal to Vn I1 is equal to Vn minus V1 divided by 1 kilo ohms. So it's just equal to 1 minus 0, which is just 1, divided by 1 kilo ohms. So I1 is equal to 1 milliamps. And likewise, we know that in the ideal op amp, there's no current that goes into the op amp. So therefore I1 is equal to I2. So I2 is also equal to 1 milliamps. Now to find V out, we can say that we can just do a KVL in this direction. So V out is equal to V in minus the voltage drop here. So it's I1 times 1 kilo ohms minus the voltage drop here, which is I2 times 10 kilo ohms. So V out is equal to 1 minus I1 is 1 milliamps times 1 kilo ohms, it's just 1, and then minus I2, which is 1 milliamps times 10 kilo ohms, so it's 1 milliamps times 10 kilo ohms. These milli and kilo cancel, and oh, so 10 kilo ohms, so this milli and kilo cancel, so it's just 10. So 1 minus 1 minus 10, so this is 0 minus 10 is equal to negative 10. So it's 1 minus 1 is 0, 0 minus 10 is negative 10, and it's important to realize this is inverting configuration, so we expect the output to be inverted, so it's minus sign. So we have found V out. Oh, we found V2 already. Oh, and in the process there was also, we are trying to find V1. And V1, remember, was just from the short circuit. So this is V1. And oh, maybe this was saying is finding out V in. Well, yes, that's also 1, so it's here. So okay. And find out what is IL. Okay, so to find out IL is just this voltage minus this voltage divided by this resistor. So is IL is equal to V out minus 0 divided by 1 kilo ohms. So IL is equal to negative 10 divided by 1 kilo ohms. So IL is equal to negative 10 milliamps. And what about finding out as IA out? Well, if we do KCL, it is the summation of all the currents entering the V out node, summations to 0. So we have I2 is going in, so going in means has a minus sign, and I out is also going in, which means having the minus sign, but IL is leaving V out node, so it is having the positive sign, and summation is to 0. So that is negative 1 milliamps minus I out. We don't know what is that, we're solving for that, plus IL is minus 10 milliamps equal to 0. So negative I out is equal to 1 plus 10 milliamps. So I out is equal to negative 11 milliamps. Now we are finding out what is the voltage gain, which is V out divided by V in. So that is negative 10 divided by 1. Units are volts per volts. To solve for current gain, IL divided by I in, plug in IL is negative 10 milliamps. For I in, so as you can see here, I in is the same as I1. So instead of write I in, we just write I1. So then it's equal to negative 10 milliamps divided by I1. I1 we found was 1 milliamps, so then current gain, IL divided by IN, is equal to negative 10. Units are amps per amps. Then last thing to solve for is power gain, P out divided by P in. Yeah, I guess that's also like called efficiency in some cases, but this time they're calling it power gain. So you do V out I out divided by V in I in. So V out is negative 10 times I out is negative 11 milli divided by V in is 1 and I in is 1 milliamps. I in is same as I1. So the milli cancels. We are left with power gain P out divided by P in. Power gain is equal to 10 times 11 is 110 divided by 1. So the units are watts over watts.